I want to draw your guys' attention to your two final analysis assignments. So first, both of them are due this week because we are ending all of our material this week. So you will be able to finish your analysis by the end of this week. First up is a plausible reaction. We're learning reactions with alkenes, alkynes, alkyl halides, and alcohols. So if you have one of those functional groups in your compound, then you can propose a reaction with it. And there's two ways that you can propose a reaction. I'm giving you that choice. These reactions don't need to be things that are reported in the literature. They don't need to be things that you could feasibly do in the lab. They just need to be things that work on paper, because that's what our class is. Things that work on paper. You can either do a synthesis where you take your compound and you turn it into something else. You take a functional group on your compound and you react it in a way that we're covering in class and turn it into a new functional group, a new compound. Doesn't need to be a compound that is useful. Doesn't need to be a compound that exists. It just needs to be a reaction that occurs. Or you can do a retrosynthesis. Find a functional group in your molecule that you can synthesize using reactions that we've seen. So if you have an aldehyde, well, you might take an alkyne and do hydroboration oxidation to hydrate that alkyne into an aldehyde. We've learned how to make aldehydes that way. That's a way that you can do it. Or you could have an alkene that you do ozonolysis with, reductive ozonolysis, and you cleave it into that aldehyde. So you have two options, but what you'll need to do first is look at your compound and identify the functional groups. Wait, you've already done that. So then you need to identify the functional groups that you've either seen how to generate or seen how to react with. And this is an all or nothing assignment again. I'm going to have you submit it as many times as it takes until you find a reaction that works. So get started on it. See if you can't already find a way to make your compound or change your compound and get it submitted. I think I've got one submission that came in last night. I haven't looked at it yet, but I'm excited to. This is a first ever for this class. I've even done this whole analysis thing in the past, but I've never had it involve a synthesis. But this is the crux of organic chemistry, is doing reactions with compounds. So I want you to imagine a way that your compound can be made or transformed. And the last part of this analysis series is a reflection. I'm not looking for a page here. I'm looking for maybe a paragraph, maybe two. But what I want is some true self-reflection and feedback on the assignment, I guess. I want to see what this project meant for you in terms of connecting with the material, making sense of the chemistry we're learning on the board in a real-life application. So you should be able to submit that. I don't want to see submissions for this, though, until you've submitted Part 4. I'm all right if you need to resubmit Part 4, keep resubmitting your synthesis, but I want you to finish that before you write this reflection. They're due at the same time, but please don't write your reflection and then try to go and do Part 4, because Part 4 is meaningful to this. I just couldn't lock this assignment until Part 4 was done, so we have to do it this way. Any questions on that? All right. A couple of reactions that I want to cover, but they actually revolve around organohalides. So I want to do a quick overview on organohalides and things that we can do with them, things that we cannot do with them. Organohalides break down into a few different families. Alkyl halides, vinyl halides, and aryl halides. There is another class in there, but I'm going to explain how it's kind of a mix of the first two and the similarities that it has, differences that it has. Alkyl halides, these are our sp3CX bonds. And these are going to be a main stake when we get into substitution reactions. We're going to learn about two types of substitution. SN1 and SN2. And alkyl halides are incredibly useful for those two types of substitution reactions. Vinyl halides. These are sp2CX bonds. So for example, vinyl chloride. If you guys have ever worked with PVC, polyvinyl chloride, this is a precursor to it. Vinyl chlorides, being sp2 hybridized, cannot go through SN1 and SN2 substitution. So I just want to make it clear, if you have an alkyl halide in your compound, you're trying to propose a synthesis with it, and you want to apply the substitution reactions we're going to learn about in a little bit, it won't work. And I'll send it back and say, this is the wrong type of organohalide to do substitution on. There are ways to do substitution here, but it actually requires a very different route that you'll learn more about in Open 2. Aryl halides. This is another sp2CX bond, but for example, here is bromobenzene. And for the same reason as vinyl halides, the hybridization of the carbon, the orientation of its molecular orbitals, this also cannot go through SN1 or SN2. Instead, you'll learn in OCHEM 2 more about how these go through SNAR, where AR stands for what? Aryl, aromatic, yep. So this week, we're going to learn about SN1 and SN2. We're going to explain why they're named that. OCHEM 2, you'll learn more about nucleophilic aromatic substitution, which is a different mechanism, requires different reagents, has very different conditions. The only thing I might say about the aryls, again, this is an OCHEM 2 reaction. You can do some sort of substitution by doing organometallics. For the vinyl halides. That's an OCHEM 2 reaction, though. All right, now the third class, that is kind of a hybridization of alkyl halides and vinyl halides. These are called allylic halides. So to be allylic, that halogen must be attached at an sp3 carbon that is adjacent to an alkene. That's the definition of allylic, which is why I see it as a combination of these two. You cannot have an allylic halide without an alkene, but you also cannot have an allylic halide without an sp3 hybridized carbon. this is our allylic position. And in terms of SN1 and SN2, these are great. And I did misspeak when I said that was the only other category, because we can make a similar combination between alkyl halides and aryl halides. Benzylic halides are similar to allylic halides, an sp3 carbon halogen bond, but rather than being placed next to an alkene, benzylic halides are placed next to an aromatic ring, the benzene ring. Notice that aryl halides cannot do SN1 or SN2, but benzylic halides are great for SN1 and SN2. Only the organohalides attached to sp3 hybridized carbons can undergo SN1 and SN2 reactions. sp2 organohalides cannot go through SN1 and cannot go through SN2. All right. Any questions on just these classifications?
Under the allylic halides, you drew a little blue dot.
Mm-hmm.
Reference, that's what
The allylic position. Yep. And similarly up here, this little black dot, that's the benzylic position. It is kind of interesting. The benzene ring carbons are not benzylic. It is carbons attached directly to the benzene ring that are considered benzylic. The benzene ring's carbons are aryl carbons. Carbons attached to the aryl carbons are benzylic carbons. It confuses people because here's bromine attached to a benzene. They want to say that's benzylic, but it isn't. Benzylic is adjacent to the ring. Haley?
I think I missed this, but what's the SN1 and SN2?
We're going to cover those this week, probably today. So this is just kind of a precursor. When we do reactions with organohalides, we will not do reactions with vinyl or aryl halides. And because you guys have an analysis assignment coming up where you have to propose a reaction, I just want you to recognize you can't apply the reactions we're going to learn to these types of functional groups. But come back for my OChem 2 class and you can. All right. Questions on this? Let's do a quick review. Ways to prepare alkyl halides. So you know what? I think let's rephrase that. Instead of alkyl halides, let's make it more generic as organohalides, because we did see some ways to make vinyl halides with our alkyne addition reactions. So these are all previously seen reactions. Rather than giving you examples, we're just going to kind of name them. HX addition to alkenes. What classification did that give us? What type of organohalide did that give us? Alkyl halides. HX addition to alkynes, which we saw in 1 equivalence or 2 equivalence forms. The 1 equivalence, HX addition to alkyne, gave us vinyl halides. The 2 equivalence, HX addition to alkynes, gave us alkyl halides. We saw X2 addition to alkenes, and we saw X2 additions to alkynes, once again in one equivalence or two equivalences. X2 to alkenes gave us vicinal dialkyl halides. X2 to alkynes gave us trans vinyl dihalides or tetrahalide products. And the last one that we saw was X2 in water or alcohols, reacting with only our alkenes, not our alkynes. How many of you spent some time last week making a table of all the reactions we've covered, looking at the functional group change? Does this seem similar then? This is just a few words summation of all of those reactions. And these were all previously seen reactions. But we have some new reactions to cover. Am I missing any on here, by the way? Can you guys think of any from your tables that you made? Okay, me either. So I think that means we're on the same page. The next reaction we'll look at is radical halogenation. And we're going to break this down into a few subtypes. First, we'll say, what happens when we do radical halogenation with an alkane? We've actually seen this already briefly. Here's our generic reaction. Say I have this alkane, and I take Br2 and light. H nu there represents ultraviolet light. The product that I get is the most substituted alkyl halide, and I get a byproduct of HBr. When doing a reaction like this, we actually want to avoid using Cl2. We'll have preference for using Br2. Chlorine is more reactive than bromine, which means the regiochemistry of the product is harder to control. Chlorine will add just about anywhere, regardless of how stable it is. But bromine is less reactive and more selective. So bromine will always add selectively at our most substituted position. So the regiochemistry of this reaction, we get the most substituted alkyl halide. The stereochemistry, if you create a chiral carbon, it's going to be created randomly. All you're doing is substituting a hydrogen for a bromine, which means that that new bromine may take on an R configuration, it may take on an S configuration. If that's the only chiral carbon in the compound, then you get that 50-50 mixture in enantiomers. If there's another chiral compound, or another chiral carbon in the compound, then you're going to get diastereomers that form. Now there's something about this mechanism. We've already viewed this mechanism, if you guys remember back in section 6, when we reviewed organic reactions or overviewed organic reactions, we actually looked at the mechanism for this reaction. We said that this reaction began with initiation. And that was simply bromine splitting apart into 2 bromine radicals. Notice the fishhook arrows. 1 electron moving at each arrow. The 2 electron bond splits in half. Homolytic cleavage. Then we saw propagation. That's where 1 radical reacts to create a different radical. In this step, 1 bond breaks and 1 bond forms. Usually I only need 2 arrows to show that, but because my CH bond is breaking homolytically, I have to have 3 arrows here. The Br radical forms a bond with the hydrogen, taking 1 electron. The carbon takes the other electron. Gives me a carbon radical and HBr. Why does this radical form? Why does the bromine take this hydrogen? There are 9 hydrogens that are attached to primary carbons. There are 2 hydrogens attached to the secondary carbon. There's only 1 hydrogen in this molecule that is attached to a tertiary carbon. So why does the bromine go to that 1 hydrogen? There's a much greater statistical chance that bromine takes a hydrogen from a primary carbon. There's 9 times as many of them. Why does bromine selectively go here? To react with that carbon to create that carbon radical. It must be the most stable product. It must be the lowest energy product, intermediate. It must be the easiest to form. What else forms the most easily when it's most substituted? Carbocations form at the most substituted position. So this follows carbocation trends. Most substituted carbon radical, I'm going to abbreviate that as a C dot. The most substituted carbon radical is the most stable. That's why we get the regiochemistry that we do. It's just like saying Markovnikov addition, except Markovnikov screwed us over by saying H adds to the carbon with more H. When really he should have said a carbocation forms on the most stable position and a radical forms on the most stable position. So now you can predict the regiochemistry. What's the last step in this reaction? Termination. So I've already formed my byproduct. I'm not going to show it again in this last step because here all that happens is my carbon radical and my bromine radical share their electrons together. Terminating. Terminating the radical reaction. I have kept this mechanism stoichiometric. I've shown only the equivalences of atoms that are needed to explain the overall reaction. But I want you to remember that these molecules do not exist in isolation. At any given time, there are hundreds of thousands of millions of other molecules. Which I think, to be clear, hundreds of thousands of millions is just a way of saying hundreds of billions. Hundreds of billions of molecules surrounding these molecules. So is this termination step the only termination step that could happen? No. Br radical could find another Br radical and terminate, which would just form Br2, but that is a plausible termination. A carbon radical could find another carbon radical, and they could terminate, which wouldn't be ideal because that would make a different carbon chain. A carbon chain I'm not hoping for. There's a lot of different terminations that can happen. This is the termination that leads us to our final product.
Can you remind me what causes the two bromines there to separate?
Yes. Actually, does anybody else want to take this? What causes the two bromines to separate? It's the light. That ultraviolet light pushes the sigma pair electrons into the sigma star, splits them. All right, that's what happens if we work with alkanes. What if we work with alkenes or aromatic rings? Okay, I've got two things here. I think I need to make this one a little bit different though. I want you to see that there is some similarity to these two molecules and the generic molecule I gave for the alkanes. That is, they all have primary carbons, tertiary carbons, and secondary carbons. So we're going to be looking at regiochemistry here. When these react with Br2, and there's actually a replacement reagent that you can use in these benzylic and allylic positions. Instead of Br2, you can use something called NBS. But anytime you use NBS, you can just use Br2. NBS stands for N-bromosuccinimide. It's a source of radical bromine. That's what NBS is. The regiochemistry with alkenes or aromatic rings present is not to the most substituted carbon. The regiochemistry is to the benzylic position or to the allylic position. If we want to look at the byproducts that form here, of course, anytime you use Br2, one of your byproducts is HBr. But if you're using NBS, then the byproduct is simply this amide that forms, or this diamide that forms. So, regiochemistry. Allylic or benzylic halide. Once again, with the stereochemistry, it's random here. If you make a chiral carbon, you will make both configurations. So the question is why? We explained the regiochemistry of radical halogenation to alkanes. Can we explain the regiochemistry of radical halogenation to alkenes and to aromatic rings? What was the explanation for regiochemistry here with alkanes? It forms the most substituted alkyl halide because
Most stable. Lowest energy.
the most substituted alkyl halide is the most stable.
Most substituted carbo radical.
The most substituted carbon radical intermediate is the easiest to form. Therefore, the most substituted alkyl halide forms. So what can be our explanation here? Because this carbon radical is not more substituted than if it was here. And this carbon radical is not more substituted than if it was here. So it's not regiochemistry, it's not the most substituted carbon radical that forms is now the most stable. What's our explanation? Resonance. This carbon radical is conjugated to the aromatic ring. Can someone help me define conjugation again? An uninterrupted series of atoms with p orbitals. So sp2 or sp3. I think most of you would look at this radical and you would say that this carbon has 4 electron regions, the ring, the isopropyl, the hydrogen, and the radical. And normally we take 4 electron regions and we say sp3. But if this carbon is sp3, then it cannot be conjugated because to be conjugated, every atom must be sp2 or sp, must have a p orbital. If this atom is sp2, then the ring starts to share in the resonance. And what's more stable than a more substituted radical? A radical that does not exist at one place, but a radical that is delocalized across a molecule. How can you make it react if you can't pinpoint where it is, if its nature is spread out over a larger space? And how would you draw arrows to relate those two resonance forms? Radical electron in, that forms a double bond. And then a radical electron out. That forms the new radical. And how many more resonance forms are there? Two more. This radical can move to this position, and then lastly, it can move to this position. So there's a total of 4 resonance structures. What about here? This radical comes in, this radical comes in, a new pi bond is made, this radical comes out. So my resonance form in my allylic compound looks like this. And those arrows just look crazy, don't they? It almost looks like nothing's even being communicated. That's it. Those are the 2 resonance forms for the allylic position.
after the radical forms, then it undergoes, or then it forms as this resonance structure.
That's correct. Neither of these resonance forms exists, but these are the two best ways of representing those resonance forms. So what do you think forms more easily? Let's do this example problem. Are there allylic or benzylic positions in this compound? Okay, so I'm not going to pay attention to anything that's not allylic or benzylic. How many positions are allylic? Just one. Adjacent to the alkene. How many positions are benzylic? Two. One here, one here. Where is it most likely to substitute? Which is a more stable intermediate, the benzylic radical or the allylic radical? Benzylic has increased resonance, better stability. So it's not going to substitute at my allylic position. That's not the easiest radical to form. Then between my two benzylic positions, should I guess that I get two structural isomers, or can I predict one major product? Would one of these benzylic positions form a radical more easily?
Does substitution play like a secondary role?
Exactly. Substitution plays a secondary role to resonance. So, the tertiary benzylic position. So if we draw out this product, that's my main isolated product, the most substituted benzylic position. We just played two things into account. First, maximize resonance. Second, maximize substitution. That's where you can predict structural placement, regiochemistry. Okay, you guys all right with that? There's another radical reaction that involves halogens, but this is not radical halogenation. Notice that all of those examples substituted a hydrogen for a halogen. So you have halogenated, and you use X2 to do so. The next reaction, I lost track of my numbers. I think we were on 7. There's two ways that you can call this. We can call it radical HX addition, or you can call it anti-Markovnikov HX addition. And we're going to see this work for both alkenes and alkynes. And of course, when we look at alkynes, we have to decide, will we consider just one equivalence of HX reacting, or will we consider two equivalences? The key difference here in the reagents, HX, as we know, does not form radicals. So there must be another reagent present, something that can create radicals on its own. This is what we call a radical initiator, hydrogen peroxide, or really any peroxide, ROOR. These are great radical initiators. If I have one equivalence of HX in the presence of my peroxide versus having two equivalences of HX in the presence of my peroxide, I get two different products. Here, I'll get the least substituted alkyl halide. H adds to the more substituted carbon, X adds to the less substituted carbon. Here, I get the less substituted vinyl halide. And here, I get the less substituted geminal dihalide. So if we talk about regiochemistry, we have to say that it's anti-Markovnikov. There's not much to say about stereochemistry. This reaction rarely produces chiral centers, but when it does produce chiral centers, they're random. The other thing we can say about regiochemistry, it's really only relevant down here. We'll always form a geminal dihalide. That HX addition with alkynes, we always form geminal dihalide as well. So now HX in peroxide, still geminal. Okay, so let's take a second to recognize that this reaction produces radicals, and it produces carbon radicals. So where are those radicals? Well, if I've got a less substituted and more substituted carbon, the carbon radical always forms on the more substituted position. So that means there must be a radical intermediate here at this secondary position and here at these secondary positions. But if the carbon radical is forming on the more substituted position, that means that the less substituted position gets its group first. So we're not going to look at the whole mechanism, but I do want to walk you through what happens. First, I'm going to look at just the hydrogen peroxide. Hydrogen peroxide readily splits open into two hydroxide radicals. It's those hydroxide radicals that are able to react with HBr. So unlike with radical halogenation, I don't get two equivalences of bromine radicals. Here I only get one. And it's that bromine radical that interacts with the alkene. Propagation. where will the radical propagate to? The less substituted or more substituted carbon? More substituted. This is the step I think you guys would like to see the arrows for. Bromine radical forms a bond with a carbon radical, breaking the carbon-carbon pi bond to make that carbon radical intermediate. And now that we've added bromine to the less substituted position, and we have this carbon radical, this is when another equivalence of HBr comes in, essentially protonating that carbon radical position. But if that carbon radical bonds to H, what's left over? Bromine radical. This reaction is a very cool demonstration of a cyclic propagation. The alkene reacts with bromine radical to create a carbon radical, which reacts with HBr to form a bromine radical, which can go find another alkene to make another carbon radical, which can find another HBr to make another bromine radical, which can go find another alkene, which can make a carbon radical, which can go find another HBr. And it just keeps cycling until all of the reagents have been consumed. So you can actually demonstrate this, this type of cyclic process by showing this. If you introduce HBr here, then you'll kick out your main product here. And it just keeps cycling through until everything is consumed.
So does the hydrogen peroxide break by light as well?
Mm-hmm. Exactly. And you guys know hydrogen peroxide is fairly dangerous. It's not something you want to deal with in like high concentrations. You can use it to clean wounds and stuff. It's a disinfectant because of how reactive it is at forming radicals. You had a question though? A follow-up? Oh no, Rustin.
So a bromine radical, is that the same thing as bromide?
No. Bromide is an anion with 4 lone pairs and a negative charge. Bromine radical is neutral. Carbon radical is neutral. Oxygen radical is neutral. Bromine radical is probably more reactive than bromide, the anion. But certainly reactive in different ways. Okay. Other questions that you guys have here with anti-Markovnikov HX addition? No? Okay, let's do a couple of multi-step synthesis problems, shall we? I want to take methyl cyclohexane, and over the course of a series of reactions, I want to make 1 bromo 2 methyl cyclohexane. This is not one step. This will be multi-step. For now, we may need to fill in some of the blanks with just generic reagents. We're going to elaborate on those reagents more today. What can I do with that starting material? Any alkene addition reactions I can run? Sorry? I think you had it. Can I do alkyne reactions? Can I prepare an alkyne? Can I prepare an alkene? Can I do any sort of elimination? Elimination requires what? Halogens. Look back at the way we prepared alkenes and prepared alkyl halides. We had an X there, a halogen group, that got eliminated. Dehydrohalogenation. Do I have an X on methyl cyclohexane that I can use? So, what should I do? Alkylation? I think I need an alkyne
No, I said addition.
addition. But there's no pi bond for me to consume. So I can't do alkene addition or alkyne addition. What reaction can I use where alkane is the starting material? Radical halogenation. So I'll take this starting material. I'll react it with Br2 and light. NBS, not a great choice when there's not an allylic or benzylic position. Br2 is the way to go here. Can I predict what product forms? What's its name? What's its regiochemistry? Does it attach to the methyl group? With the methyl group? That kind of feels like the same thing. Can you describe the substitution of the carbon you're trying to describe? The bromine adds to the tertiary carbon. Adds a bad word, sorry. The bromine substitutes at the tertiary carbon. I need Br2, not HBr, because one of those equivalences of bromine is taking away the hydrogen. So I get a byproduct here of HBr. All right, now we've gotten here, and we might not know exactly where to go from here, but I bet that we could find a way to get that compound. What type of reaction could I do? What precursor would I need to get up to that product? You guys have done questions like this before, especially with the HX addition reactions. So I could have an alkene that is down here. And what alkene, where would that position of the double bond need to be? What alkene could I use to get up to this product? How many possibilities are there? There's really only two possibilities. I could have an alkene here, tri-substituted. And if I did HX addition, that would give me this product. More substituted Markovnikov addition. But if I did HX with peroxide, that would give me anti-Markovnikov addition. Or my alkene could be here, could be di-substituted. In which case, HX addition would give me a halogen forming here, or a halogen forming here. Because in HX addition, this carbocation rearranges. So if I have an alkene here and I do HX, I never get the compound I want. If I have an alkene here and I do HX with peroxide, I get this product plus the structural isomer where the bromine adds on the other carbon, because the two carbons are of equal degrees of substitution. So, what's the best bet? Try substituted alkene, HBr with peroxides. That gives me my selective anti-Markovnikov addition. I want to point out to you guys that what we have just done is 2 of the 3 main ways that I recommend solving multi-step syntheses. And I want to lay these out for you guys because this is how I want you to try and solve these problems. Multi-step synthesis. Tips. The first thing I often tell students to do is to label their carbons. Actually, better than label, I tell students to map their carbons. Mapping means I don't need to number every single carbon, and I don't need to number them in any sort of IUPAC way. Mapping is just a way of making sure that I have everything connected where it should be. We talked about mapping when we looked at alkylation. I don't really think I need to map them here because nothing's happening that much. I'm not gaining carbons, I'm not losing carbons. The second thing that I recommend doing is brainstorming. We did this when we said, what can we do with an alkane? Can do radical halogenation. Can I do any alkene addition? Can I do any alkyne addition? That's kind of where we got stuck. Then we looked at the last one and we brainstormed. What different ways can I make that final alkyl halide? The third tip that I give, the last tip, is to work forward and backwards. I would say we got it easy here in saying that the starting material really only has one thing that it can do. It can go through radical halogenation. But then we also worked backwards. We tried to figure out what precursor makes that final product. We worked forward to figure out what the starting material can make, and we worked backwards to figure out what can make the final product. And now we've got ourselves here, where there's 3 steps, there's 2 intermediates, and we just have to figure out what gets us here. Anybody have an answer for that? No. Not. HX will not be a reagent. What type of reaction is happening here at this step? Addition, elimination, or substitution? Elimination. Formation of an alkene. So what type of reagent should I add here? A base. Now we haven't gotten any more detailed than that. A base. But that's what I need. I need to deprotonate a carbon. I need to remove a hydrogen from it. And in that same step, it will form a double bond and kick off the bromine. All right. Now that was challenging for sure. What I'd like you guys to do now is solve this synthesis. I'd prefer if you solve it in groups.
When you put the multi-arrows, that just means there's more than one step.
That's right. Those 2 arrows just means more than one step is involved.
But it doesn't necessarily just one way.
One more time.
It doesn't necessarily just mean one error. The amount of errors doesn't mean just multiple.
It doesn't tell you how many. That's correct. I made a mistake here. So I need to recount my carbon chain. Okay. If it helps, I'll map these so that when you're copying it down, you know that you've got the right number. Try to work with people around you so that you guys can collaborate on finding reactions, brainstorming, working together forward and backwards.
Oh, you remember? Yeah, that's fine. So we can have another person. But it looks, I mean, it's a good light, because like I know goes from, okay. Oh, wait, no, sorry.
I'd say 4 steps here.
Okay. Yeah. And would this one go
Are you brainstorming? What reactions can be
without
done?
what is said with this stuff right here? What reactions? Like with the, okay, this start. That would be. I'm just like.
Okay, I'll give you a hint because I think this might not be obvious. You can actually utilize this starting material in 2 different ways and join them back up later in the synthesis. So utilize this starting material to do one thing and utilize it to do something else that can then react together. Or just don't think about that and follow through on one synthesis and figure out what needs to be added otherwise. It can be. Well, if you found it, you'd realize it wasn't actually random. Not if it's an alkane. Alkanes really only react through radical halogenation. Alkanes don't do well in alkylation.
Yeah. Yeah. So I feel like that's. I know, I need to with the
Oh.
so I was like, I kept going. Was it like an 8? No, I'm
Good, good.
I feel like last step. They're
Hey, John.
Hey.
Why can you not just
Yeah, you can. But you need to, if you realize how to alkylate it, then you can actually figure out that it can be used in two different ways. It can be used to make the compound that is substituted.
Okay, so because you put 2 arrows there,
No,
that means that
no.
there's
2 arrows is just saying more than one step is required to do
so
this.
we have to find a way that does not have to.
You can use alkylation. No, alkylation has to be a step of it.
How is that not the only step?
Because I'm telling you that whatever you're going to alkylate this with can be made from this as well. And this is vague. This is not a question I put on a unit test or anything like that because it's not clear how many things you need to do. What I would have said, if I had done better, I would have said, prepare this final product only using this starting material in whatever ways you need to, keeping in mind that you can use it to do 2 different things. Let's say you've got 100 milliliters of this in the lab. Take 50 milliliters of it, do one set of reactions. Take the other 50 milliliters, do another set of reactions. Dump them together when you're ready. But a lot of you have already gotten to this point in your brainstorming. You're thinking that alkylation will be a part of this. So if you think alkylation is either the first step or the last step, that's part of your working forward or backwards. Figure out how to incorporate alkylation into this.
So you're saying we have to form we have to form the alkyl halide that we would alkylate with from the starting material?
That's right. Yeah, I agree. That's good.
I woke up late today. I've just been so behind. I'm like,
Well, you're not alone.
I'm looking at this right here. I'm trying to remember where this random.
Well, you don't have numbers here, so it should be 1, 2, 3, 4. First step, deprotein. Second step, adds the methyl. Third step, deprotein. Fourth step, adds the benzyl.
So
You need to have 1, 2, 3.
right, there's your CH3 X, CH3
Well, the X could be chlorine or bromine or iodine. That doesn't matter as much. Work backwards. What can you make that from? Map your carbons. Where are those 10 carbons in the starting material?
In order to then alkylate this or that.
All right, guys, I think some of you have stagnated a little bit, so let me tell you how I would map this. I'm going to start by mapping those 5 carbons to the starting material here. Because what I see is that carbon 5 is part of an internal alkyne. So carbon 5 could have been alkylated by a terminal alkyne. Now I'm actually going to use another set of colors here because I'm also going to map this way, 1, 2, 3, 4, 5, which actually maps exactly the same. So carbon 5 in green is going to be a nucleophile. That means that I need to deprotonate my starting material, make it into that alkyne anion that is a nucleophile. And carbon 5 in green will substitute carbon 5 in red. That is going to be my final step. That means that carbon 5 in red needs to have a group that can leave. I could make that Cl or Br. I have a preference for Br in general. Carbon 5 in green needs to come in as a nucleophile. So I could show this a couple of different ways. I could just show it already as a nucleophile, and I could have a little arrow that shows how I made that nucleophile. Or I could take this alkyne and show it with the reagent that makes it a nucleophile. That alkyne plus sodium amide will deprotonate it. These two things don't exist together. It looks like this. Substitution by a nucleophile. Green 5 attacks red 5. Alkylation. That's my last step. What I just did there was worked backwards. But now I actually have a better idea of how to work forward, because I think you guys would agree there's 9 different ways I could take this starting material through alkyne addition reactions. But I know that I need to get it to this structure where 4 has 2 hydrogens added and 5 has had 1 hydrogen, 1 bromine. How am I going to do that? Can I do HX addition twice? First of all, HX addition gives me Markovnikov addition. That would add bromine to carbon 4. I want to have bromine added to carbon 5. So if anything, in my brainstorming, I know that I need anti-Markovnikov HX addition. I need radical HX addition. But if I do HX in peroxide twice, I get a geminal dihalide. But I don't want a geminal dihalide. I just want an alkyl halide. I want 1 halogen there. So I need a way of adding hydrogen across the pi bond and HX across the pi bond anti-Markovnikov. I should do this in 2 separate reactions. Hydrogenation and radical HX addition. So that would be the other thing that comes across in my brainstorming. I'll need hydrogenation here in order to get this structure. So tell me, what are different ways I could do this? How could I incorporate hydrogenation and radical HX? So 1 equivalence, HX 1 equivalence with peroxide, and then H2 with PDC. Or H2 with Lindlar's catalyst to make an alkene, and from the alkene, HX with peroxide. Or sodium in ammonia to make an alkene, followed by HX with peroxide. So there's 2 routes that I could go, and in one of those 2 routes, both of my partial hydrogenations work. Here's what I envision. H2 with Lindlar's, or sodium in ammonia, because these are very good at getting me down to my alkene. The only reason I say this is what I would want to do is because if I was doing it in a lab, I would want to make sure I don't have to worry about the equivalences of HX that I'm measuring out. And then from here, HBr with peroxides. Hydrogen peroxide works there, H2O2. Generic peroxide works there, ROOR. And then just to clarify, the other route that also works is HX, 1 equivalence with peroxide. And let's just say HCl, which gives me this. And then from HCl, I can do H2 with PDC. Because it doesn't matter what my leaving group is. It doesn't matter that my halogen is bromine or chlorine. Both of these react in the same way to give that final product. If you guys look at the practice final exam, I have a reaction roadmap. You have to fill in reagents and compounds, intermediates. And there's some spots where you have reagent, intermediate, and reagent that all have to be filled in, which is essentially solving a multi-step synthesis. You have to figure out how to do that transition. And it looks something like this, where the same starting material is used in two different ways to create this longer carbon chain in the final product. What do you guys think about this multi-step synthesis? Interesting? Challenging? This is where a lot of professors will say they're testing you on your critical thinking. How well can you take all of the reactions that we've learned and couple them, sequence them, use them in tandem with each other? And I might argue that this is creative thinking. You need to be creative about how your functional groups can transform, what atoms you can place where, how that changes their reactivity. Critical thinking and creative thinking, I think, are the same thing. If you can think critically, that usually means you're thinking creatively. You're imagining all of the different options. But this is not easy if you don't know the reactions. And how do you get to know those reactions better? You've got to practice. You've got to spend time with it. And a good way to do that is to make a table. Yeah.
Is there like a reference table on Canvas? Because whenever I try to Google one, it's like everything.
I don't have a reference table. Maybe I sent an example from my OChem 2 class though. Anybody sound familiar? No? I might be able to find one that an OChem 2 student has made. But it is up to you. As you start building it, you'll figure out what the best way is to craft it. If you're planning on just copying a table, it's not going to do you any good. It's not going to be as good as working it out on your own.
Sam, are you ever gonna have us identify like what the best reaction would be, or just any feasible reaction? Because you said like you could have just done the one equivalence of
Oh.
HBr.
Yeah, both of those would give you full points.
So you just need to know if it's possible.
Correct.
And not if it's like the most convenient way or whatever.
Correct. Yeah. Some might say, I don't want to use mercury sulfate to do hydration of an alkyne because it's not convenient for me to work with mercury. That's fair. Find another synthesis. Here, where there are two routes that are of equal lengths and they give the same product, both are totally valid. There is an idea about the most efficient synthesis. So we could have taken this alkyne, hydrogenated it to an alkane, radical halogenated that to an alkyl halide, put that through elimination to make an alkene, and then done anti-Markovnikov HX addition, and then done substitution, alkylation. Just adds a lot of steps. That's not incredibly efficient.
You still not get right.
If you get to the final thing, I will give you credit for it. There are professors that I've seen though who think number of steps is an important component. Other times I actually tell you how many steps I'm expecting it to have. Here's a starting material, here's a product. Give me two reagents and an intermediate that connects them. So if you give me additional steps beyond that, then you would lose points because you didn't find a way to do it in the steps provided. But not a lot, especially if you get to a complete reasonable synthesis.
I know that for some reactions that we don't have the mechanisms down, do you just want us to like memorize like what the products are and like the reagents are for those?
I would encourage you never to memorize anything. But to be familiar with the transformations, which does feel like memorization. Familiarization and memorization are, the only difference is practice and application, in my opinion. I think for every single reaction that we've learned, you should be able to predict the product without needing to try and go through the mechanism. It will only slow you down to prove a mechanism to get to the final product. That's why with every single reaction, I give you this regiochemistry, stereochemistry, so that when you look at starting material and reagent, you can say, okay, look for the more substituted position. Look for anti-addition wedge and dash, or syn addition, 2 wedges. Yeah? So I don't want you to memorize how to do it, but that is kind of the process. You should be able to make that step without having to show the mechanism for it. Mm-hmm.
I know you said you don't want us to, just copy a table because that doesn't necessarily help us internalize all these.
Internalize is a good word, yeah.
But I'm wondering if there's a place somewhere other than the lecture recordings where we can access all of these to be able to make our table with.
The textbooks, a lot of textbooks report all of the same reactions. If you look at our textbook, Carey, it will actually not mention the alkene hydration reaction, oxymercuration reduction. It will only reference that after the supplemental problems at the end of the chapter. Because it says in the textbook, nobody wants to work with mercury. And then in the alkyne chapter, it just throws in mercury for the hydration of the alkynes. So I called their BS on that. So that would be one place where if you look in the textbook, you might not actually find the reagents themselves. But otherwise, almost all of the free online textbooks that you'll find on LibreText, they'll have all of these reactions too. Different textbooks organize them in different orders. So you'll have to just kind of sift through to find the ones you want.
But this set of reactions is pretty standard.
Very standard, yeah.
So we're not looking at like a selection that might be unique to our class.
True. There are reactions you'll find in textbooks that we didn't cover. Those are not things I would expect you to go out of your way to learn, because you're not going to see it in my class. All right. So usually at this point, I like to say we've looked at all the different ways to prepare alkynes and alkyl halides, and we took some tangents to look at multi-step synthesis because this is an important application of all these reactions. But this is where I would normally say, let's look at reactions with alkyl halides. There's really going to be 2 reactions for us to consider here. Elimination. Our generic reaction here, we've actually seen it already. If I have a halogen and a hydrogen, and I expose them to a base, then I can run elimination. And I get this alkene. Now there are 2 types of elimination reactions. E1 is first order elimination. Jamie, when we say first order, what are we speaking to? This is reaction rates, reaction kinetics. We're saying that this reaction, the rate of this reaction, how quickly this reaction pumps out product, depends on one compound. And that one compound here is the alkyl halide. Once that compound is set up and ready to react, then the elimination proceeds quickly. That's what first order means. There's two compounds of interest, the alkyl halide and the base. Doesn't matter how much base you have in E1, only matters how much alkyl halide you have. So there's a couple of things that I want to say here about E1. The regiochemistry of E1 is referred to as Zaitsev. Zaitsev was a guy just like Markovnikov, and he said when an alkene forms in elimination, it is the most stable alkene that forms, which is the most substituted. Another important thing for us to note about the regiochemistry of E1 reactions. They produce carbocation intermediates. This is the hardest thing for the reaction to do. The alkyl halide separates, and it produces a carbocation. That takes a lot of energy. But once that carbocation is formed, then it quickly reacts to give an alkene with the base. We also have to recognize that if there's a carbocation intermediate, there can be structural rearrangements that lead to an even more substituted alkene than just the regions around the alkyl halide. In terms of stereochemistry, if a stereocenter forms, E1 prefers the lowest energy, the trans alkene. So, if applicable, the trans alkene forms. Now, we have to clarify what base means here as well. So we've talked about the regiochemistry and the stereochemistry of the E1 reaction, but the base is what we call weak. That's going to be things like water and alcohol. You know, we have another word for things like water and alcohol. Those are polar protic solvents. So if water is acting as the solvent and the weak base, that means that you're running a reaction with the solvent, and we call that solvolysis. All right, the other type of elimination reaction is called E2, short for what? Second order elimination, which implies what? Two compounds that impact the rate of the reaction. Both the alkyl halide and the base. Increase the amount of alkyl halide, your reaction goes faster. You make more product. Increase the amount of base, your reaction goes faster. You make more product. So rather than a base that is weak, a base that only reacts once a carbocation intermediate forms, E2 has a base that is strong, a base that wants to take a hydrogen, a base that runs the elimination. So the amount of both of them impacts the reaction rate. The regiochemistry, actually, I'm going to do this a little bit backwards, if you guys don't mind. We're going to look at the base, and we're going to say that this is a strong base. And that's things like hydroxide and alkoxides. Alcohol's conjugate bases, RO minus. It's not an oxide because it's attached to an alkyl group, so it's an alkoxide. But there are two types of strong bases. There are small bases and there are bulky bases. Bulky just means sterically strained. Steric strain occurs with more substituted things. So some examples of our small bases: hydroxide, methoxide, ethoxide, CH3O-, CH3CH2O-. Our strong base that is bulky, the most common example that we'll use is tert butoxide. And there are a few different ways to draw tert butoxide. Just like there's a few different ways to draw these other bases as well. Can you tell me why tert butoxide is bulky, but methoxide, ethoxide are not bulky? Why is this bulky and these are not? Yeah. Tert butoxide has those 3 methyl groups, creating a ton of steric strain. Remember when we talked about rings, we said the tert butyl group always causes the most strain. Whereas methoxide, ethoxide, much less size going on, much less steric strain. So when we talk about the regio and stereochemistry of these reactions, we need to distinguish them based on their size. The regiochemistry of a small base is considered Zaitsev. This goes for the most substituted alkene. The most substituted alkene requires taking a hydrogen from the most substituted carbon. Taking a hydrogen from the most substituted carbon requires getting into where there is the most steric strain. Small molecules can fight that steric strain at the most substituted carbon, but this bulky base cannot fight the steric strain. It's bringing steric strain of its own. So the bulky base gives us anti-Zaitsev, which is often called Hoffman. 2 guys fighting for the same regio directive. With stereochemistry, these reactions are what we call anti-periplanar, or antiplanar. That just means that the hydrogen that is removed and the halogen that leaves must be in the same plane as each other, and they must be anti to each other from a Newman projection. I'm not really sure what peri means in there. Antiplanar sums it up pretty well. And that's true for both of these, whether it's a small base or a bulky base, is that these must be antiplanar. Then, if possible, then it prefers a trans-alkene. But I do want to make it clear, this is stereo-selective. If there's no way to get a trans-alkene via an antiplanar conformation, then there is no trans-alkene that can form. But if there are 2 possibilities of an alkene, then it prefers the trans-alkene. When we come back in tomorrow, we're going to look at examples of elimination reactions and how we can apply small base versus bulky base to try and control the regiochemistry of our elimination. All right? Then we'll look at substitution reactions with alkyl halides. Enjoy the rest of your day. I'll see you guys tomorrow.